Hello, good afternoon, everyone. I'm Dong Jindong from National Cheng Kung University in Taiwan. Welcome to today's seminar organized by the Coastal Zone Risk Mitigation and Management Working Group of AOGS. I was invited by Professor Yip to moderate the talk today. So today we are pleased to invite Professor Dong-Ju Peng for a talk. Professor Peng's research institute lies on detection and attribution of regional sea level changes. Professor Peng received her PhD degree in astrometry from Graduate University of Chinese Academy of Science and started her career in satellite orbit determination and at the Shanghai Astronomical Observatory in China and the Royal Melbourne Institute of Technology in Australia. Professor Peng also spent 1 year with in a research center, Ligos in France. So currently, Professor Peng is a senior research fellow at the Earth Observatory of Singapore. So Professor Peng's particular research focus to study the coastal sea level rise in Southeast Asia and associated impact of climate change, natural hazards, and human interventions. So today, Professor Peng will give us the talk entitled Innovative Use of GNSS for Sea Level Studies as Sub-daily, Seasonal, and Long-term Timescale. So let's welcome Professor Peng. Professor Peng, is your time now? Please.
Okay, thanks, Professor Dong, for your introduction. And thanks, Professor Yip, for inviting me. So today I'm going to share my work. Okay. So today I'm going to share my work of using GNSS to study sea levels as sub-daily, seasonal, and long-term timescales. GNSS stands for Global Navigation Satellite System. It is a general term describing any satellite constellation that provides positioning, navigation, and timing services. It consists of GPS, owned by the US, GNSS, owned by the Russian, Beidou, owned by China, and Galileo, owned by the European Union. Those four are global GNSS. There are also there are also two regional GNSS. One is Indian IRNSS. It is designed to cover the Indian region. The other regional GNSS is QGSS, owned by Japan. It was developed to complement GPS for the coverage of East Asia. GNSS measures the distance of the satellite transmitter to the antenna. If the measurements are perfect, we will need only 4 GNSS satellites to determine the position of the antenna. Why 4 satellites instead of 3? It's because there are 4th parameter, the clock bus of the receiver, that needs to be determined together with the position X, Y, Z. So we will need at least 4 satellites to know the position of the antenna. But like any other measurements, there are errors in the GNSS measurement. The sources include the clock bus from the satellite and also the orbit errors, allospheric delay, tropospheric delay, and also the noise in the GNSS receiver. There's another one called multipass. Sometimes we also call this reflections. So when we are performing precise positioning, these errors can be either modeled or estimated, except reflections. Why reflection are ignored in positioning? It's because it is environment dependent. There is no generalized model. it is also elevation angle dependent. The lower the elevation angle, the stronger the multipass. And they are different for different frequencies. So we're not able to cancel out the multipass errors by combining different frequencies. So the commonly used approach to mitigate the multipass errors is simply to use an elevation mask. For example, using data with elevation angle greater than 7 degrees. In this talk, I'm going to show how we can turn these errors in positioning as useful data in sea level monitoring. GNSS multipass is generated when a satellite signal reaches the receiver from 2 or more passes, one directly from the satellite and the others reflect from nearby buildings or other surfaces. This figure is a schematic, shows the GNSS multipass reception in urban scenarios. For example, if a receiver or GPS receiver is located in between 2 buildings, it can receive signals directly from the satellite and also signals reflected off the building. What if the obstacle is water surface? So if the antenna is placed near the water surface, it will receive signal directly from the satellite and also signals reflected off the water surface. And these reflect signals will interfere with the direct signals, and this will create a pattern which will be recorded in the signal to noise ratio data. Here is an example of how a GNSS satellite signal from an antenna near water surface look like. This is just one satellite pass over a station, so it lasted around six hours. And we can see from the high elevation angle, the SR data is quite clean. But at the low elevation angle, like both ascending and descending arcs, we can see fluctuations. This is a reflection from the water surface. If we fit a polynomial for the SR data, we can think this as a direct signal and remove it from the raw SR data. Then we can get the oscillations at the low elevation angle. So we can see at both ascending and descending arcs, the patterns are quite clear. So this pattern can be modeled as a function of the distance between the antenna and the water surface. This schematic is just an example to show the correlation between the height of the antenna and the frequency of the multipass data. The higher the height, the higher the frequency. From this equation, we can see if we want to calculate the height, one of the commonly used approach is inversion. In this case, we want you to estimate all the parameters, include amplitude, phase, and also the height. But for this particular case, there is another way to calculate the height, that is spectrum analysis. This is because we know the main reflection source is a water surface. So the dominant frequency will be from the water surface reflection, and this frequency can be determined by spectrum analysis. So my research is use this spectrum analysis to determine the height of the antenna and then convert it into sea level time series. Here I'm going to use a station located in the US as an example to show how the spectrum analysis works. So this station located in the US, Alaska. This photo shows the station at low tide and high tide. So I take 4 satellite data as an example shown in this figure. So we can see in this figure for the 4 satellites, the common thing is the dominant frequency of the multipass or SR data is distinguishable from other frequencies. So we can easily convert the dominant frequency into reflector height. So that is the height between the antenna and the water surface. So I take this 4 satellite as an example and convert the convert the reflect height into the sea level. So from this photo, we can see the height of the antenna is anti-correlated with sea level. So this is a conversion of the reflector height to relative sea level and compared with the collocated tide gauge observations. The tidal range at this site is around 8 meters. It's quite large, but GNSS IR beautifully captured the high tide and low tide sea level change and match well with the tide gauge observations. Speaking of tide gauge, it is one of the two most commonly used systems for measuring sea level. This photo is a historical tide gauge at Alaska. So at all days, if we want to know the water level at tide gauge, we will need someone to read the numbers and write down the numbers every 1 or 2 hours. Thanks to the advance of technology, tide gauge have been automatically operational since 1833. This schematic shows how a modern tide gauge works. So the tide gauge will measure the sea level relative to a local datum. This datum is determined by other sources, like, for example, GNSS or leveling, and this datum has to be maintained regularly to keep it accurate. The advantage of tide gauge is it has very long records. For some stations, the record lengths are greater than 100 years. And from this figure, we can see the tide gauge is attached to the land. So it measures both the surface height change and also the land height change. Another issue of tide gauge is the spatial coverage. So this figure shows the global tide gauge. The blue dots are the sites with record length greater than 100 years. We can see most of the sites with longer record is located in the northern hemisphere. And in sea level community, there is a consensus that at least 60 years data are needed for robust sea level trend estimation. So all these white dots, which is with data record length smaller than 50 years, cannot be used to estimate the global average of sea level rising trend. Only the blue dots and some of the red dots can be used, but most of them are located in this area, and very few are located in the southern hemisphere. So the global average of sea level trend could be biased using this data set due to the poor spatial coverage. The other system commonly used for measuring sea level is satellite radar altimetry. The first satellite was launched, TOPIX was launched in 1993, and afterwards we'll have GSM-1, Envisage, GSM-2, and some GSM-3 and Sentinel-3 satellites. And I'm sure in the future there are more satellites continuously to measure the global sea level change. So for example, this is a satellite imagery satellite. It carries a radar sensor which measures the range between the satellite and the surface, and it also carries GPS or DORIS or satellite laser ranging to determine the position of the satellite. So we will know the position of the satellite relative to an ellipsoid. So if we subtract these two, the satellite altitude and the range between the surface and the satellite, we will get the surface height change. The advantage of satellite radar altimetry is global coverage, and also it measures the sea level relative to the center of the Earth, which is just a geocentric sea level, which is a very important indicator of climate change. But the problem is the measurement of satellimetry at the coastal zones are not yet reliable. I will talk about this later. So compared to tide gauge and satellimetry, GNSS have a much shorter history. It was only demonstrated to be capable of measuring water level around 10 years ago. And I started working on GNSS to study sea level around 5 years ago. Shortly after I started to work on this topic, Adam, a professor from US, Constance, the PhD supervisor, asked me this question: is GNSS interferometric reflectometry effective in monitoring storm surge? Why ask this question? It's because strong winds are associated with storm surge. So the strong winds will make the surface rough, and the surface roughness may prevent the coherent spectral reflections and potentially make GNSS fail. At that time, we don't know whether GNSS is able to detect sea level change under such extreme event. So here I'm going to show an example of Typhoon Hato. For this event, the highest wind speed reached 50 meters per second, and the highest surge height reached 4 meters. Shortly after this event, US deployed a team to survey the flood area in Macau. This is Constance from US doing the survey. While we are doing the survey, it's because all the tide gauge in Macau are failed to record the peak water level change. And Adam's team is going to model this event. So any data about the peak height will be useful to his team. So he asked this question, but unfortunately, we didn't find any GNSS in Macau that can be used to detect sea level change. But we found one in Hong Kong. Hong Kong is also affected by this extreme event. This station is co-located with a tide gauge. So this is a tide gauge house. This is the GNSS station called HKQT. And we checked both the GNSS and the tide gauge will function normally during the Typhoon Hato. So it's a perfect site to do our test. So we used the GPS data to retrieve the water level change during this period. The blue dots are our results. The green line are the astronomical tide, and the red line are the tide gauge observations. We can say that our results match well with the tide gauge observations, and the storm surge is above the astronomical tide is also quite clear. But we didn't publish our results because it was just one example. It's difficult to convince people. But the next year, another even stronger typhoon hit Hong Kong again, and our GPS data also captured the storm surge height. So we published these results, and this is the first paper to demonstrate GNSS is effective in monitoring extreme sea level events like storm surge. So in 2020, there's another strong storm surge called Hurricane Nora in the US. Christian Nelson's team used the GNSS data to track the change of the water surface. So this figure, the color dots are from the observations from GPS GNSS Ganil, and the blue line are the tide gauge observation. And this gray area shows the wind speed greater than 30 meters per second. We can see the GNSS determination is quite effective up to the point when the wind speed is smaller than 30 seconds per meter. But still, we can see the GNSS successfully captured the peak height. Why? It's because the eye of the hurricane passed directly over the site. So this is a wind speed sensor co-located with the GNSS. We can see there is a sharp drop for the wind speed. So that's why the GNSS can capture the peak height of the storm surge. GNSS also been demonstrated to be able to track the tsunami. So this is an example from the 2020 earthquake. This is a tsunami model showing the maximum amplitude reached 50 centimeters. So, and in this area, there is a GNSS station located at the at the affected area. So this is the results. The dots, blue dots, and the green dots are the GNSS results, and the green line is from a tsunami model. This is for regular GNSS data processing. We can see the GNSS results does not match with the tsunami. What's the reason why they didn't match? It's because during tsunami, the surface is changed quite fastly. So we will need to apply a surface rate correction. So after apply this correction, we can say GNSS results match well with the tsunami model. And also, the authors calculated the surface velocity. The velocity from GNSS also match well with the model results, tsunami model results. So GNSS-IR is able to be used to track the tsunami. For larger event, we don't know yet, but for tsunami like this, this level, GNSS is able to track the peak water level change. Another advantage of GNSS-IR is it measures sea level relative to both the land and a reference ellipsoid, which is constant with the satellite imagery. So this is a schematic figure. So for GNSS antenna, we can determine the height relative to the land using the reflected signals, and we can determine the position of the antenna relative to ellipsoid using the direct signals. So if we subtract these two, we can get the surface height change, which is consistent with the satellite altimetry observations. To test this theory, we use the same site located in the US, and this site has been demonstrated to be useful for sea level monitoring, but the goal of the paper is to validate the GNSS-IR results using tag gauge observations, and also they only used 1 year data in their paper. So for our paper, we use longer data, 8 years data, and our focus of the paper is to measure the coastal absolute sea level change. So first, I'm going to show the relative sea level change. The blue dots are our GNSS results relative to the land, and the red is the modeled annual cycle change. So we can see at this site, the annual cycle is the dominant seasonal sea level change. After removing the seasonal sea level change, we get a falling sea level at a rate of around 10.4 millimeters. Why it's falling? Because all the news tell us sea level is rising due to global warming, but at this site it's falling. And we have a further look, and we found that actually at this site, the land is rising at an even greater rate, 12.7 millimeter per year, due to the combined effect of elastic and viscoelastic response of the Earth to the mass loss of the glaciers and ice field, because this site is located quite near to the Greenland. So after we convert the sea level relative to the land to the sea level relative to the ellipsoid, which is absolute sea level, we get a rising sea level at a rate of 3.2 millimeter per year. We also compared our absolute sea level, the amplitude of our absolute sea level change from our GNSS and also the trend with the satellite imagery observation. For the most correlated observations, we can see both the amplitude and the trend match well with the satellite altimetry observations. This demonstrates the potential of GNSS-IR to measure coastal absolute sea level change and tie together on land and offshore observations into the same reference frame. And also, GNSS-IR may have the potential to fill the observational gap in coastal zones. It's because we know tag gauge is inside observations. It can only sense the sea level change in specific locations. And for satellite altimetry, due to the land contamination. So at coastal zones, which is around 10 to 15 kilometers near the coast, is not yet reliable. For GNSS-IR, so this is a GNSS located in Singapore. The height is around 5 meters above the water surface. So we can say actually the GNSS can sense the sea level change extending to the 100 meters away from the coast, and it senses actually the sea level change from an area instead of like tag gauge is just a specific location. So GNSS-IR may potentially fill the observational gap in coastal zone if we have like enough GPS placed near the coast. And in this example, because the height is only 5 meters above the water level, so the distance is only 100 meters. But if we place the GPS at a higher location, it can sense the sea level change up to 1 or 2 kilometers further away from the coast. Besides using the existing GNSS data, we also install our own GNSS station. So our first GNSS station specifically installed for sea level monitoring was installed in Taiwan in November 2019. This is our team from US performed installation, and thanks to their hard work, we have this beautiful time series from GPS, GNSS, and Galileo. This allows us to investigate the issue of GPS orbit leakage in tidal estimation and how to mitigate the bias. First, let me explain what is the GPS orbit leakage. So this table shows the periods of the 8 major tidal constituents. We can say the period of the K2 tidal constituents is coinciding with the GPS orbit period, and the K1 the periods of the K1 tidal constituents coincide with the GPS revisit period. So the coincidence of the K1, K2 periods with the GPS orbital period will cause geometric errors in the reflection data, consequently resulting in bias in the K1, K2 amplitudes estimated from the GPS-IR sea level measurements. GNSS, Galileo have different orbital period, so they may overcome this issue of GPS orbital leakage in tidal estimation. So we use our site as example to test this hypothesis. So our station is located in Taiwan, and at 2.5 kilometers away there is a tag gauge. So we use both the GNSS and tag gauge to do tidal estimation and compare these two. So for GNSS, we use data from the blue. The blue bar is the GNSS results from GPS. The red is from GNSS. The yellow is the results from Galileo. So this is the amplitude difference. This is the phase difference. This is the absolute difference between the GNSS estimation and the tag gauge estimation. We can say most of the 8 major tidal constituents match well with the tag gauge estimation, except the GPS results. So this is due to the geometric errors in the reflection data. So if we combine the GPS data with GNSS or Galileo and GNSS together, we can say the difference between the GNSS result and the tag gauge immediately reduced. So this proves the use of GNSS or Galileo can mitigate the bias in the GPS-IR result for estimating tides. If we combine these three, we will have a better temporality, and we will have a more robust estimation of tides. Singapore also has a GNSS work. It was developed by the Singapore Land Authority for operational use like positioning and tracking. Two of the stations, SSTS, SNSSC, are located in a very good location, and that can be used to measure water level change. So we are collaborating with the Singapore Land Authority to use their data to study sea level change. So first, let's have a look at the location of Singapore. So this area is Singapore. It's located in a sharp transition zone, resulting in very complex tidal dynamics. And also the monsoon winds flowing from South China Sea will interact with the tidal currents and further add to the complexity of the tidal regime. We know that the two GNSS stations is located at the east and west of the Singapore, and right in between the two GNSS stations there is a tide gauge. So these three stations may potentially capture the transition of the tides and also probably capture the monsoon effect on sea level change in the Singapore Strait. So we combine sea level from GPS and GNSS to estimate the tide. So we can see the M2 and S2 tidal amplitudes in the Singapore Strait increase westwardly. Actually, the length of the Singapore Strait is only 20 kilometers. So it's a very short strait, but the change of the tidal amplitude is around 10 centimeters. It's around 10 centimeters. So normally we don't expect tidal change so much in such short distance. This is the special, the unique features of the tidal constituents in the Singapore Strait. We also calculate the daily relative sea level change at the three sites. We can see at SNSC and the TP, they match well, and they both the amplitude and the phase. But compared with the SSTS, which is located here, so both the amplitude and phase are a little bit different. This is because of the location, because South China Sea is over here. So the wind flowing from here, from South China Sea to the Singapore Strait, this STS is located further away. So it is shielded from the wind straits from South China Sea. So that's why it has a smaller annual amplitude. My research is focused on sea level change, but GNSS is not limited to study sea level. It has been demonstrated it can use to study soil moisture. So this is a site located in the US. The color dots are the water content derived from the GNSS, and the green area are the 5 soil moisture sensors, and the black line are the average of the 5 sensors. The blue bar are the rainfall observations. We can see the color dots is the GNSS results match well with the soil moisture sensor observations, and after each precipitation event, we can see a sharp increase of the soil moisture from both the soil moisture sensor and GNSS results. So GNSS is potentially useful to study water cycles. It has also been proved that GNSS can be used to measure slope depths. So this is a site located in Alaska. It is co-located with a pole. This pole is used to record the slope depths. So like the old tide gauge, we wanted someone to read the numbers regularly to know the slope depths, and they compared the manually rated slope depths with the GNSS results. They match quite well. So GNSS is also useful to measure slope depths, but it's automatic. We don't need to to do this manually regularly. So we will save a lot of labors. Christine also proved the GNSS can detect volcanic plume. So this example. So if the volcano is located here, if it erupts, it will generate a plume. And if the satellite pass, if the receiver here and the satellite happen to pass this plume, so the signals will be disturbed by the plume. So we can use this information to derive the plume height. So this figure shows the SNR data before and after the eruption. So we can see the change of the SNR data. So this can be used to derive the plume height and also the shape of the plume, which will be used for volcano monitoring. I'm sure there will be more applications of GNSS waiting to be discovered, but my focus will still be considerable for the next couple of years. So we are going to install more GNSS stations for signal monitoring in our region. So far, we have planned 4 stations in Singapore and 1 more station in Taiwan. Actually, before the pandemic, we had some discussions with Vietnam, Thailand, Indonesia, and Malaysia to install our stations, but all this are disrupted due to the travel restrictions. So we were going to restart our collaboration with our neighboring countries to install more stations near the coast to monitor both the sea level change and the land height change. Okay, thank you for your attention.
Thank you very much, Professor Peng. Very nice talk and very interesting. You introduced this GNSS technology, not only for sea height measurements, sea level measurements, you also introduced some more application for stone search and tsunami measurements and snow depths, soil moisture measurements. Is interesting and looks very wide application by GNSS. We are now have 13 participants online. Now I think we open for questions or discussions. Now is 4:40 in my countdown. So I think we have around 10 to 20 minutes can have questions. So anyone has comment or questions? Please open your mic and then you can give your question for Professor Peng.
Oh, I saw a question from the chat. So which program did you use for the processing of GNSS data and for the SNR modeling? I use my own program because when I start to work on this technique, there's no code to be used. So I developed my own code by collaborating with Christina Sen, the developer of this technique. I know she has released a software called GPS reflection, but I'm not using her code. I have my own code to do all my research, but I'm following her code and her progress for this technique.
Okay, there's another question by Brian. Hello, thank you for a nice presentation regarding the detection of chronic from what chronic characteristic is GNSS able to detect? Right?
Okay, so personally, I don't do research about using GNSS to detect the volcano plume, but from Christine's paper, she used the SNR data to detect the plume height.
So plume height.
Yeah, plume height.
Check. Is any more question? That's one earlier question. Program is already answered. Sorry. Professor Ip, in the very beginning, asked one question. Do you think Macau is particularly vulnerable to tsunami?
According to a paper from published by US, yes, it's vulnerable because Macau has reclaimed a lot of land, so this may enhance the vulnerability of the tsunami hazard.
So that means we should move out of Macau, right? Tongju.
Sorry, can you repeat?
I mean, so we should move. People should move away. Should leave Macau altogether.
Oh, no. But the study shows it's like a very extreme scenarios. So we don't know it will happen or not. But at the extremely bad scenarios, it may have very bad impact. But we hope that will never happen.
Okay.
And I have another question about your, at the very end, you talk about the GNSS station.
Yeah.
And you have, how many you have in Taiwan now?
So we have one installed, and we will have another one will be installed next year. So actually, the second one, we have get the permit to install the second station before the pandemic, but we are not able to travel during pandemic. So we will install the second one in 2023.
So are they very useful in your work?
Yes, they're useful, and also this station actually is a station in Taiwan. So we installed this station for the purpose of sea level monitoring, but it also recorded the earthquake happened. I don't know, it's a few months ago. There's an earthquake in Taiwan, so our station also recorded the earthquake. So it's like we use for my studies, I use some existing GNSS data which is not installed for sea level monitoring, but can be used for sea level monitoring. So this station is particularly installed for sea level monitoring, but it can be used to record earthquakes.
Now, Professor Sanka from Bangladesh, I think, he's particularly interested in earthquake and tsunami. And he has a question.
Oh, okay.
Can you see that?
Okay. How many geostations needed to locate a particular event next? Actually, it depends on the location. But if we only use GPS, it's quite limited. But now we're able to, most of the GNSS receiver can receive other GNSS like Galileo, GLONASS. So I think we will for the Taiwan station, the temporal resolution is around 10 minutes. So I think for like storm surge, if it lasts around 2 or 3 hours, we will get it's like more than 20 observations. I think that's enough to constrain storm surge monitoring.
Yes, I think that Professor Peng, Dad, you has a question, right?
Yes. Please. Professor Feng Chen Dart, please open your mic. You can ask your question now. Yeah.
Yes, thank you. Hi, Dongju. Very nice to see you. How are you?
Good. Long time no see. How are you?
Very glad to very nice in presentation about the new technique to measure the sea level. And concisely today we have a class, and you can see the big screen behind me, and I show the talk, and I show the talk to my students, and they very enjoyed. And they had two questions for you.
Okay.
The first question is, we know that we have some other techniques that can measure the sea level, such as the high frequency data, HF. Okay, so they would like to know the difference between GNSS and the HF radar in terms of measuring sea level. Can you explain it to me?
Yes. First, their accuracy is different. So it's like the high frequency radar is more accurate than GNSS, but one of the advantage of GNSS is it can be installed at a higher place. Unlike the radar, it has to be installed near the surface. For example, the extreme event like I showed in Macau. So under this extreme event, this can be damaged and they cannot record the peak water level change, but GNSS can. So that's one of the differences. Accuracies are different, and also like the requirement for installations are different.
Okay, so the installation for GNSS is much simpler than HF data radar.
I think it's simple because for the radar package, it needs to be regularly maintained. I don't know. It's like I don't know the price, but to my mind, it's more expensive than GNSS. And also, it's like for radar, it can only be used for sea level monitoring, right? But for GNSS, it can be used for both sea level monitoring and land height change. So, because for tide gauge alone, it cannot separate the two effects, surface height change and the land height change. But with GNSS-IR, we're able to separate these two because with one equipment, we're able to measure the both change of the surface height and the land.
Yeah, I see. Yeah. For following your answer about the difference between GNSS and HF data, my student also would like to ask you in extreme weather. I believe you answered a bit in your previous answer, but he would like to know whether GNSS can withstand to the strong typhoon.
Oh, okay. So under that extreme events, we know it's like because of the strong wind, it will make the surface rougher than normal time. So this may, because for GNSS-IR, the principle is specular reflection. So if the surface is very rough, so the principle may change. So the specular reflection may fail. So it depends on it's like how strong the wind is. So for my case in Hong Kong, in Taiwan, so we can track the storm surge up to the wind speed around 40 meters per second. But the example in Christine's paper, it's up to 30 meters per second. So if the wind is greater, the wind speed is greater than 40 or 50 meters per second, we'll be not able to use GNSS-IR to track the storm surge.
I see. Okay. All right. Thank you very much for your presentation and your answers. Thank you.
Thank
hope to
thank
see
you
you
for,
again soon.
okay. Thank you for coming.
There's one more question in chat window.
Okay, could you also provide
tsunami risk report based on all measurements?
No, not yet, because I only focus on the GNSS-IR technique, to use this technique to derive the height of the antenna relative to the water surface, but I'm not able to do tsunami modeling. So I wanted to collaborate with someone whose expertise is the tsunami modeling.
Any more questions?
You know, I just wanted to ask a simple request. Can we have a PDF of your talk?
PDF.
This slides, basically.
Yeah. Probably can. Yeah, can.
Yeah. Okay. So, can we download from somewhere? Can you write it in the chat?
Okay. I can send it to Professor Ip probably, and
Yes,
he can.
yes.
I can.
In the chat, I have given my email in case you can send it.
Okay.
Right.
No problem.
Thank you very much.
No problem.
Thank you. Any more questions? Professor Peng, I have one short question. That just like the slide you show on the screen, this receiver looks installed very high above the sea level.
Yeah.
And in one of your earlier photo, the station in Alaska is very very close to sea level. So what's the height sensitive inference? Is this height the sensitive for the receiver installation of the height for the readout?
Okay. Okay, so it's like ideally we want to install our station as high as possible relative to the surface, because with higher height we can sense the sea level change further away from the coast, and we know there is a observation gap in coastal zones. So if, for example, there are stations located in the US, it's around 300 meters above the water surface. So it can sense the sea level change around 2 kilometers from the coast. But this is a very particular case. So it's very hard to find this kind of place to install a GNSS station. So we usually install our station that is used to the location that is easily to be accessed. So for this station in Taiwan, we had to do a very hard site selection, and finally found this site which is around 16 meters above the surface. So that is almost perfect for sea level monitoring. So, but one of the differences is if we install the station at a high place. So, for example, if it's 30 meters above the water surface, then we will need high rate GPS data. For example, if 5-second data or 15-second is not frequent enough to be able to be used to sense the sea level change. So if the station is only around 5 or 6 meters above the water level, the 50 seconds data is adequate enough to do the sea level retrieval. So this can save a lot of storage, but if we want to install this to a higher place, we will need higher rate data. So we know it's like 1 hertz data needs a lot of space to store. So that's one of the issues.
Thank you. Okay, so any more questions?
Yes, I wanted to just, this is not a question, just a query. Could this GNSS-IR is able to predict the magnitude of the tsunami in terms of height, if you measure the height of the tsunami?
Predict? No, GNSS cannot predict. It can only just like retrieve the height. It's like in the past. It cannot predict because we will need to do the modeling to predict. So, but the height from the GNSS is useful to constrain the tsunami model.
Okay. Thank you.
Okay, thank you for your question.
Thank you. So anyone still question? Okay, if there's no question, I would like to close today's talk. If someone still have question, I'm not sure somewhere you can find Professor Peng's email, and you can write an email to her. I believe Professor Peng will really like to discuss with you. So thank you very much for the audience, especially thank you, Professor Peng, for your very nice and very wonderful talk for today. So I would like to close the section now, and thank you, and wish you have a nice coming Christmas time. Merry Christmas. Thank you, everyone.
Thank you. Happy holidays.
Bye-bye.
Thank you so much.
Thank you, everybody.
Bye-bye.
Bye-bye.
Bye.